Hello everyone, I'm Naimul from University of Maryland. My co-author is Niklas Elmqvist from Aarhus University. I'm glad to present Dataopsy, Scalable and Fluid Visual Exploration using Aggregate Query Sculpting or AQS. Visualizing today's real-world datasets from the Facebook social network to the billion parameter large language models is more or less impractical when using a representation that insists on using one mark per data item, the so-called unit visualizations. This fact is exacerbated by today's trend towards using small mobile screens. And finally, even if we had enough pixels, there is a limit to the number of data items that the human perceptual system can interpret effectively. What is truly needed to tackle the next generation of data visualization challenges are techniques that are born scalable or that have been designed to be scalable from the inception. In this paper, we propose such a born scalable visualization technique that we call Aggregate Query Sculpting or AQS. Unlike typical overviews containing thousands or millions of data items, the initial AQS view is a single substrate containing a single supernodes. From this point off, the goal of AQS is to provide the user with a set of fluid interactions to split the supernode into smaller data subsets during exploration, similar to how a sculptor will iteratively cut a large piece of clay into pieces to shape and mold separately. There are six such interactions in AQS. The first one is pivot. Pivot splits a supernode into n disjoint supernodes. For example, we could imagine pivoting a dataset of curves based on the number of cylinders, resulting in 3 new supernodes. The partition operation is a pure visual operation for laying out supernodes in 2D space along a vertical or horizontal geometric axis. This approach is similar to pivot graphs or Polaris, but supports nesting in multiple levels. If the chosen geometric axis has already been used for partitioning, the next level of partitioning will be nested. Sometimes the user wants to see inside a supernode without pivoting or partitioning. The pick operation transforms the supernode into glyph representations showing the contents of each mark based on some axis. For example, picking can change the color-coded circles into pie charts showing the origin of each group of curves pivoted and partitioned based on the number of cylinders. Piling merges two or more selected supernodes into a single supernode, potentially enabling the user to name the resulting supernode. For example, the user could choose to pile the 0 to 10 and 10 to 20 gas mileage supernodes into a single supernode that they named Poor Fuel Economy. Partitioning multiple pivots into the same geometric axis will eventually yield deep nesting and an explosion of supernode combinations. To reduce clutter, the project operation enables selecting a subset of the data and projecting it into a new semantic substrate. For example, the user could select all of the low fuel economy curves and project them into a new substrate to enable further exploration while avoiding to add to the existing nested hierarchy or partitions. Finally, the prune operation allows for eliminating selected supernodes from the view. We developed Dataopsy, a web-based visual analytics tool, to demonstrate AQS in practice. Dataopsy can be used in a standard web browser using any medium to large screen device. For example, the figure shows Dataopsy on a Samsung Galaxy S8 tablet device. Let's see a demo of Dataopsy now. For demonstration purposes, I'm going to use the adult income dataset. The dataset contains 45,000 data points. Here, the prediction task is to classify if a person's income will be greater or less than 50,000. After loading the dataset in the tool, we can iteratively partition the initial view by different attributes. For example, let's partition the horizontal axis by train and test set and vertical axis to male and female individuals. We can add race on the vertical axis, We can hover over circles and axis levels to interact with the visualization. We can then use the picking operation to see the proportion of accurate predictions in for each subset. Here, the green color indicates correct prediction, wrong otherwise. We can select subsets of choice and project them in a new view. This creates a new view with selected data points. Note that the histogram here has only one bar as all data points appear exactly once in the dataset. We can now partition this dataset using new variables. For example, we can partition the vertical axis by marital status and horizontal axis by education level. One useful operation here is piling, which lets us combine different categories together. For example, we can create two new groups, people having a before college degree and people having a postgraduate degree. We can now see accuracy across the subsets. To evaluate Dataopsy and AQS, we conducted several case studies and application examples. For the first case study, we worked with two data scientists and fairness researchers to explore how AQS and Dataopsy can be used to evaluate fairness of an ML model. Participants used the adult income dataset we have seen earlier to identify performance of a logistic regression model across different social identities such as gender, race, and occupation. Overall, participants easily found the subsets where the model was performing poorly. Participants also performed data analysis tasks such as finding empty subsets efficiently using Dataopsy. In the second case study, a creative writer used Dataopsy to navigate a complex set of scenes, locations, chapters, and characters from a fictional novel and sculpted it for adaptation to a screenplay format. The critical challenge of writing an adapted screenplay is to decide what plot lines, characters, or places from the original story to include in the adapted story. Using Dataopsy, the writer was able to see how characters are connected to each other in the original story. The writer then used the prune and piling operation to design the skeleton of the screenplay. As an example of large-scale analysis, we analyzed 1.7 billion taxi rides in New York City to identify hotspots for rides. We started by pivoting the taxi rides by the years. The number of trips has gradually declined over the years. We then selected 430 million trips from 2016 to 2019 and partitioned them by their pickup and drop-off boroughs. As expected, most taxi rides originated and ended in Manhattan. We can further project the Manhattan trips in a new view and partition these trips by their pickup and drop-off zones within Manhattan. Our final example is a scientometric analysis of IEEE VIS publication using the VIS-pub dataset. This example was designed to show how AQS can be used to analyze multivariate network. We can explore this dataset at different levels of aggregation. For example, the figure on the left shows a citation network between four conference tracks: VIS, InfoVis, VAST, and SciVis. On hover, Dataopsy highlights references originated at InfoVis and papers citing InfoVis papers using a light green color. AQS and Dataopsy has several limitations. For example, AQS is a top-down technique where the exploration starts with a single mark. So the users needs to have prior knowledge and hypothesis to construct the queries. Dataopsy has limitation for analyzing quantitative values. For example, when visualizing a quantitative attribute using the picking operation, Dataopsy uses binning and categorical color scale, which can be challenging to decode for quantitative variables. As a theoretical concept, AQS is scalable to any number of data points. However, as an early prototype, Dataopsy currently lacks a few engineering features, such as on-the-fly analysis of really big datasets. Finally, we recommend that practitioners and researchers adopt AQS if the following conditions are met. With that, I would like to thank you everyone and please see our paper for more details.